All right, so we have our general solution. Let me compare. Let me make a comparison here. So let's just take a breather for a second. If we had y equals x squared plus c, this c value just shifts my graph of x squared up and down. If I had y equals x minus c on the inside, that shifts it left to right. So depending on where this c value is, it's just shifting the graph. So this, if I graphed my solution, my general solution, I'm missing this c value. So I don't know where to shift it. I don't know if I have to shift it at all. If I had this 0, then I wouldn't have to shift it at all. But this graph, whatever it looks like, for different values of c, just means that I'm shifting it around. So a general solution is just some shape of a graph, like a parabola, or something more complicated like this. This is probably like something like that. It's going to be shifted around, though, depending on what c is. Now, since the solution to differential equations, since it's a function, we can say, with initial conditions, we can say, all right, solve this differential equation so that the function, so that your solution also passes through a certain point. And when they say that, when you have problems like that, it's called an initial condition that you have to satisfy. I know that's really confusing, but I'm going to write it down and hopefully it'll make more sense. So the add-on to this is find a particular solution, that's a vocab word, to the same differential equation, so the same differential equation as we had there. Find a particular solution so that y of 0 equals 1. That just means on this graph, wherever it is, it passes through 0 for the x value and 1 for the y value. So what we're going to do is simply use our general solution and plug in these values and solve for c, because c makes us shift this function around. So we want to shift it around in the exact way so that we can get it to pass through 0, 1. So that's what we're going to do. We're just going to plug in an x and a y and solve for c. Because we already have the general solution, we just need to shift it around so that we get a particular solution with this condition being satisfied. This initial condition, that's what it's called. Okay, so I'll take my general solution, y, and instead of y I'll write 1. So 1 equals -1 over -2 times, instead of x I write 0 squared, plus c, that's still on the bottom, and I'm going to solve for c. So I get 1 equals -1 over nothing plus c, so 1 over c. Multiply both sides by c, and I just get c equals -1. There we go. So my particular solution is just this general solution, with a c value of -1. So I have y equals -1 over -2x squared minus 1. That's my particular solution. And if I plugged in 0, 1, I would get a true statement here. That means it passes through that point. That's what I needed. That's it. I'll do another example in this video. So the idea is to first separate the variables and the dy and the dx, integrate both sides, and then solve for y with whatever tricks. And that will give you the general solution. To get a particular solution, you need initial conditions. If no initial conditions are given, then you can only get a general solution. That's it. And the general solution is just like a family of functions. Depending on what c value you have, decides where you would shift the function. So that's all we have for that. Let's move on to the next example. So if we're asked to solve, there are no initial conditions, so we're just going to get a general solution here. If we're asked to solve this, then what do we do first? We got to separate the variables somehow. Now some people might be thinking, oh, I don't know how to separate the variables if it's in the exponent. Oh, maybe I take the natural log of both sides, blah, 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 blah. There's something really easy to do, and it's just remembering that if you have the same base and you're dividing, that's the same thing as subtracting the exponents. So we can go from here back to here. And that's what I'm going to do. Because if we're subtracting there, that just means that we have dy dx equals e to the x divided by e to the y. Then it makes it easy. I'll multiply both sides by e to the y. So I get e to the y on the left side, dy. And I'll multiply both sides by dx, and I get e to the x, dx. So we've separated the variables in the dy and the dx, and we take the derivative, or the antiderivative, which is just taking the indefinite integral. The antiderivative of e to the y is just e to the y. Now normally, I put plus c, not even normally. Last time, I put a plus c1 and a c2, but it eventually changed to just regular c on the right side. And that's what I'm going to do here. I'm going to omit the plus c on the left side, and then this would be e to the x plus some constant. Normally, or before, I wrote a c1 and a c2, and then added over, and it changed to c. That's not what normal mathematicians do. This is the normal thing to do, because you do that every single time with the plus c. So you just put the plus c on the right side. After that, I need to get the y by itself. To do that, I just take the natural log of both sides. So ln. You cannot take the natural log separately. E to the x plus ln of c. That's incorrect. You can't do that with natural logs. Yeah, it doesn't respect addition, so you're not allowed to do that. It's not correct. So, then what? Well, I can take the y and bring it down. I cannot take the x and bring it down because we still have this plus c in there. If I had e plus c raised to the x, then I'd be able to move the x out. But I don't have that. So I can't do anything over there. This would be y times the natural log of e, and the natural log of e raised to the x plus c. The natural log of e, this is a property to remember, that's just 1. So I get y equals ln of e to the x plus c. There it is. We were looking for a function, y equals, and we got it. There it is. That's it. That's all we do. That's it. That's it.